Okay, time for the last part of the last lecture of the domain-specific languages of mathematics course for the 2022 instance. So I thought I'd end with a bit of an overview of what the domain-specific languages we've been looking at, or what domains have we been looking at languages for in this course. And generally speaking, what we defined here early on, already in first lecture, that what we consider a domain-specific language here consists of basically three things: a syntax, a semantic type, and an evaluator. So a function that translates all the syntactic expressions into the semantics, the meaning. So examples we have from all the chapters of the book, and we'll take them one by one, just briefly to remind you what they are, and maybe you will get inspired to go back and study a little more before the exam. So we started in chapter 1 with complex numbers as a bit of a case study on taking a math book quote and perhaps making fun of it, at least analyzing it very carefully. We also talked about funexp, expressions of one variable, which can represent functions of one variables. And these have been a core thread throughout the course, coming back over and over again. And also actually the types. We talked about the language of types, pair types, maybe types, function types, and how all these things build together to express syntax and semantics. Okay, that was chapter 1. In chapter 2, we talked about logic and proofs. And we started out with propositional calculus, simple proofs, things that can be evaluated to true or false, and or implication and so on. And then we took the step towards first order logic, where you got also quantifiers for all exists, and you can start talking about a domain inside your logic. We also talked about proof terms, so how to not only prove things, but also talk about the language for the proofs. What can a formal language for proofs be, and how can that be implemented? We only scratched the surface here. There are whole courses on this topic elsewhere, as with many other topics. And we also applied it to a little bit larger project about pure set theory. Not that we are especially interested in pure set theory by itself, but as an example of a domain that we can code up. And there was a use of both the logic part and the domain part, and some proofs related to it. Chapter 3, then we went straight into derivatives. The normal one argument function derivative, but also partial derivatives and applications. And we also started exploring how Haskell supports overloading and what we call type classes. So the language of types can be classified into different subsets of types. Types for numeric operations mainly that we've been focusing on. Additive, multiplicative, things like ring and field. Then we moved on to algebraic structures, the sort of mathematical counterpart of the type classes. The simplest, monoid, then group, ring, field, and so on. And we introduced the concept of homomorphism. Also, along with funexp and types, something that has been returning back over and over again. So homomorphism is a structure preserving mapping. So between different algebraic structures, or very often an eval function from a syntax to a semantics. The homomorphism then is preserving, for example, the addition in the syntax tree and transforms it to an addition and the semantic, the underlying semantics, be it that functions or sets or something like that, something else. Moving on to chapter 5, we return to something rather familiar, perhaps a bit of resting here, getting back to polynomials. But here we also made use of the algebraic structures and built up not just polynomials as functions of real numbers, but polynomials over any ring, so one of the algebraic structures that we introduced. And it turns out if you make polynomials with coefficients in a certain ring, those polynomials also form a ring. So we can define addition, multiplication, subtraction, and so on for the polynomials. And not only that, if we want to move one step further and make it also a field, that does work out if we move from the restriction of polynomials to be finite lists of coefficients to power series where we have infinite lists of coefficients. Then we can divide polynomials and get perhaps power series out. We also continue talking about derivatives because for polynomials and power series we can compute derivatives. And not only can we compute them, we can also solve certain equations using them. So we can express a power series as a recursive equation that solves an ordinary differential equation. We sort of spelled this out more clearly in chapter 6. We talked about Taylor series, Maclaurin series, derivative series in general, and expanded on this ordinary differential equation formalism. So describing how you express an ordinary differential equation and how you use power series to get at least approximate solutions for them. Moving on to chapter 7, we talked about vectors. So the concept of an algebraic structure of vector spaces, which reuses most of the algebraic structures we had from before, fields, additive, and adds just one new operation, scaling. Taking a scalar, which could be any field, so real numbers, rational numbers, or actually power series and things like that, and scaling some additive concept that we call vector. And we used the examples of finite vector spaces, but finite dimensional vector spaces, but also infinite dimensional things where functions have the role of, functions from real to real, for example, play the role of vectors. We talked about matrices. Actually, it turns out that matrices is just the syntax of linear transformations. So this is yet another example of a syntax, an evaluator, and a semantics. So the matrix, the sort of description of a column or rows of columns of numbers, or at least some field or ring objects, they represent in a short and compact form a linear transformation, which is a function between vector spaces. And then finally, just the earlier lectures this week, we talked about the Laplace transform as an example of a linear transformation, but also returning to the ordinary differential equations as a way of solving a certain class of ordinary differential equations using the transform and then normal algebraic manipulations, and then recognizing that the result actually comes from some of the well-known functions. We did the exponential, sine, cosine, and a few more. So in total, we've gone through 8 chapters of the book of domain-specific languages of mathematics. They've been filled with different domain-specific languages and also other supporting concepts. So I think if you didn't know Haskell before the course, you probably know Haskell fairly well after the course. And hopefully you will also have gained a deeper understanding of your mathematical structures, both a little bit on the algebraic side and proof side, but also on the analytical side and the relationship between them. So the last thing, I should just wish you good luck on the exam. And I do hope that you will be interested in learning more and that you will contribute if you find bugs or fixes that you think should come into the book, or maybe a future edition, or maybe a second book, domain-specific languages of, well, what do you want it to extend at? What do you want us to extend it to? Physics, climate impact research, probability theory, you name it. It will be an interesting journey onwards. But next step here is for you to learn the last few parts of the course and get a great result on the exam. Thanks for me. Bye.